Good morning students. So welcome back to digital signal processing class. In today's class we are going to continue the same concept of FIR filtering, that is finite impulse response filtering. In the previous class we talked about the linear phase filters. In that what we discussed that linear filters having h of n, you want to get it, how to get it, we convert into h of e power j omega, right? So to get this thing we took two form of it. One is magnitude form, second part of it we done with phasor form, right? So by getting the magnitude form we got it h of e power j omega we took, and we found out the response of it. Then we took the e power j theta of omega. So this j we modified into theta of omega. This j is nothing but component of it. In order to get this thing, what we did, we found the poles and we found the group delay and pole delay. So what is pole delay? We done with this. Pole delay is given by theta of omega by omega, right, with minus. Similarly, group delay is nothing but differentiation of theta of omega with respect to omega. So this thing we done and we found out the response of linear phase filter. So in that, what about this linear phase filters is all about? It is about the response of finite impulse response, FIR filtering. So since our unit 2 in digital signal processing DSP class, we did with lot of problems, right, based upon approximation techniques. What are the approximation techniques we had? We had Chebyshev, we have Butterworth, both the approximation techniques we do have, and we found out the response of it. Similarly, in this FIR filtering or finite impulse response filtering, what are the advantages of IIR? So what is that IIR filtering? It is infinite impulse response. This is finite. So in your digital signal processing lot of what we call appliances or electronic devices, what we are using FIR filtering. There are a lot of advantages is there for FIR filtering. One first advantages over IIR would be it is quite easy for designing, for recursive type of networking, for non-recursive. For both of them, this kind of filters has been used. What is recursive means? The response which keep on repeating, that is called it as recursive. Non-recursive means which has a stuck, which we just want to find the response of it, we just can't find further implementation is not possible. For that kind of filters also we can go with FIR filtering. That is one of the advantages. Second part, when you want to find out the advantages of FIR and IIR filtering, we can say that whenever we want to find the response of this FIR filtering, the most important thing what you need to keep in your mind is that its stability. So we can say that the FIR filter is more stable. So what I am saying for this, it is more stable as compared to IIR. What is the stability factor? That stability factor depends upon the filtering. How much filtering you are going to pass to this particular FIR filters. It is quite stabler than compared to IIR. The second thing what I said about recursive. So for recursive and non-recursive network, it is useful, right? That is the second point. Next thing, third point, for designing this particular filtering, we required linear phase which can be easily designed. So as I am saying, it is what linear phase filter. So this, because of we are using linear phase filtering or linear phase filters, it is quite easy to design, because that designing is depends upon your magnitude and your phasor form. So when we know both the things, it's linear means it's not fluctuating, it's not oscillating, it is having the quite constant response throughout the designing, right? For that particular thing we are saying that this is linear phase filtering, because of it's quite easy to design this type of filtering. So this is the third point, advantages of using FIR filtering over the IIR filtering. The next point what we had, it is quite free of limit cycle oscillation. So what is this meaning of that? Free limit cycle oscillation. So what is the meaning of this free limit cycle oscillation? It is nothing but whenever we had the filtering designing, we took the bilinear transformation, impulse invariant transformation for IIR filters. Those are oscillating. That oscillation depends upon two things. One is the main lobe, then we do have these are called side lobe, right? This is our main lobe. So main lobe, these are our side lobe. So these are actually nothing but the oscillations of that particular gain of the particular filter. So those are more in IIR, whereas in FIR it is free limit cycle. They don't have that much of oscillation. They may have it, but as we compare with IIR filtering, it has quite less number of oscillation in designing form. So because of that point, we can say that these particular filters are free from limit cycle oscillations. So next thing, we just want to go with proceeding with excellent design methods are available for various kinds of FIR filters. So what I'm saying, design methods. So design methods are nothing but windowing techniques. So design methods are quite easy in this, and we can say that it has a windowing techniques. So what is this windowing techniques is all about? It's having specific techniques of windowing where it is going to find out the response of the filter by taking rectangular window, triangular window, then we do have Hamming window and Hanning window. By using these particular windowing techniques, and even we do have Kaiser window. So by using these all techniques, these filters are quite easy and simpler to design the filtering concepts. Because of these all factors, we can say that your FIR filter is quite easy and quite stable and having the implication of getting easier way of designing when compared to the IIR filtering. So let us see how it is going to be used. So next students, so we just want to proceed with the second part of it. In the second part, what actually we do have, we need to see the disadvantages. So as we see that there are a lot of advantages, as we know that when compared with IIR with FIR, what we discussed that it is quite stable. Second thing, when we want to go for designing, it is useful for both recursive and non-recursive kind of filters. Third thing what we discuss is when you go for linear phase designing, it is quite easy to design. Next, fourth point what we discuss, because of these all factors, it quite easier for all kind of parameter designing. It's because of that it is useful in digital processing of the signals. So this thing we discuss. Next thing is that what is the disadvantages of using this FIR filters. Basically, when I'm saying it is used for FIR filtering, so when we see this FIR filtering, that means for designing the parameters. What kind of parameters? The parameters which are related to filter coefficients. So for filter coefficients parameters, it is quite, the implementation of narrow transition bands or FIRs are very costly and required more considerable arithmetic operations. So what is it saying? That it's saying that whenever we had arithmetic operations for digital processing of the signal, it is useful so many operations in that, because arithmetic operation means all type of operation, addition, multiplication, modulus, all the things you required, right? For that particular operation you require a lot of filtering in that. Because of that it is quite costly, so very costly for designing this particular filtering. That is the first point. That is one of the disadvantages we can say, because of the cost. Second thing, as we are saying that for the memory elements, for the designing of the memory element, it will be useful. So in that what they are saying, memory requirements and execution for that particular filters are quite high. So memory requirement, because it perform a lot of operations, because of that it required more memory. So memory of that particular filters are quite higher. So these two are the disadvantages of using the FIR filtering. So now what we say that we already said one of the advantages that for designing this thing it is useful windowing techniques. So now next method or next concept what we do have is design of FIR filter. Design of FIR filter using windowing techniques. So this is our second concept. So windowing technique. So this thing we are going to discuss now. How do we design the FIR filter? By using the windowing technique. So basically how many windows you had? So basically in your syllabus you do have windows are 5. One is rectangular window. So we'll take the rectangular window function and we'll try to find out. Second thing we do have triangular window. Next third we do have triangular, one more name is Bartlett. So Bartlett window or BARLET, Bartlett window or triangular window, both are same. Next we do have Hamming window. Hamming window. Next we do have Hanning window. Then last we do have is scatter window. Okay, so these are the methods of windowing techniques we are going to use for designing the FIR filter. So basically what it consists of, when we are saying windowing techniques, it should also have an impulse response, right? So what is that impulse response? For designing this filtering by using the windowing techniques, we are going to take the impulse response. What is the impulse function is given by h of n. For that h of n, we have to use a desired frequency response. So basically, what is the frequency response means? Hd of e power j omega. Why we are taking e power j omega? Because when we are designing the filtering, we have applied Fourier transform, right? In the previous one also I have showed you, whenever we had h of n, we just want to write in terms of h of e power j omega. For that, what we will write? What is this hd of e power j omega? This is the first step. You have to find hd of e power j omega. How it is given? hd of e power j omega is given by summation n is equals to both the sided, two-sided it is, minus infinity to infinity. Then we should use, what is the function is given? hd of n, because it's an impulse response, right? So then, and since we are applying this one by using z transform, it is e power minus j omega n. So this is your function for designing the h. What is hd of n actually? It's a continuous form. So how do we get this thing? So to get hd of n, we'll apply this formula. What is the formula? 1 by 2 pi integrating from minus pi to pi. So what actually it is? hd of n is a function of h of e power j omega. So it is h of e power j omega n and d omega, right? So we are applying like inverse. How do we apply like Fourier transform in your discrete Fourier transform? Discrete Fourier transform and inverse discrete Fourier transform. In the same way, to get hd of e power j omega, we had this function. To get this thing, we should know hd of n. It is 1 by 2 pi integrating from minus pi to pi and e power j omega n d omega. So if you get these two particular parameters of hd of e omega and hd of n, you can find this function, right? That is the first step for any kind of filtering. So basically, what is this h of e power j omega? To get these functions, we say that it is nothing but like a Fourier coefficient. So Fourier coefficients have infinite length. What is this thing? As you can see here, it is how many? It's nothing but minus infinity to infinity. That means it indicates it is a infinite length. But infinite length we can't find out. We have to make it finite. For that, what we will do? We'll go for truncation. Truncation. What is the meaning of truncating? Truncating means reducing the size of the filter. Suppose your filtering is keep on moving. It's complete having lot of signals which keep on moving. So we need to truncate. Truncate means out of that we need to take a desired one. That is called truncation. So to go for that particular thing, we have to truncate the FIR filters into infinite one by giving one factor. Small n is equals to plus or minus n minus 1 by 2. What is this capital N indicates? We know that this is nothing but sample as we have taken in the previous one. Here is, it is nothing but length of the desired sequence. What is n? Length of the desired sequence. So this is nothing but your capital N. So we have to take the value of capital N. We can find out the windowing technique of that one. And what is this capital N? We said that it is nothing but length of the desired sequence. But truncation of the Fourier series abruptly we cannot do it, means suddenly we cannot do it, which if you are doing that one, then it is called as oscillation. So that oscillation we don't want. What is the meaning of that? We are saying that we have to make n. Directly we cannot, abruptly cannot select this thing. If you select it, what will happen? Oscillation keep on fluctuating. That part we don't want. We want our signal needs to be desired one. We just want the signal needs to be a proper way of designing. For that, what we will do? The abrupt truncation of the Fourier series results in oscillation of two things. What is the oscillation of two things? We may have pass band or we may have stop band. So we cannot get the oscillation in both. We don't want that. If we want that, then it is same as IIR filtering. So this abruptly you cannot go for truncation. What I don't want? I don't want truncation. So for that, what I'm doing, in order to go for these two, if I'm getting this kind of truncation in oscillation of your pass band and stop band, that particular thing is due to the convergence of Fourier series. So Fourier series can go for conversion, means whatever signals we do have, all are coming and meeting in one particular point. That is called it as convergent. So because of these convergent concept, you may get this truncation of that pass band and stop band. That particular effect of convergence of Fourier series is considered to be the Gibbs phenomena. They may ask you in 2 marks. How do we define Gibbs phenomena? Whenever we want to reduce that, or whenever we want to truncate the signal in FIR filtering, because it's infinite length, if you want to make it finite one, we may get oscillation in pass band and oscillation in stop band. So we cannot do abruptly. We cannot change that particular sequence abruptly. If you are getting the oscillation, that particular effect is called it as Gibbs phenomena. So what we are defining by that term? Gibbs phenomena. Right? So in order to overcome from those particular Gibbs phenomena, we are proceeding with all these particular windowing techniques. So because of these particular factors, we say that we are proceeding with these windowing techniques. In that, how do we define the window? That is one criteria we should know. So first thing what we did, students, we took the HD of e power j omega. We had this formula. In that we required HD of n, because our Fourier series, what is the Fourier series all about? It convert n domain to, what is the factor here? E power j omega, omega domain, right? By using Fourier transform. If you want to apply inverse, then omega to n domain. So that's the reason here convert omega to this thing, then n to omega. So this value if you know, then we can substitute here, we can find that HD of e power j omega. So because of that, we are proceeding with next one, that is nothing but R function. What is R function? Windowing function or windowing technique function. How do we get the window? That is nothing but by taking the factor of small n. How do we define small n? It is plus or minus n minus 1 by 2. So what is the criteria of doing it? Now we are proceeding with how do we get the window. That function I'll show you. How do we get the window technique and how do we find the value of that particular windowing technique. So for that what I'm doing, I'm using one factor, omega of or W of n. W of n, suppose if it is equals to W of minus n. If you had this two condition, then it is nothing but window. It is called it as window technique by using a windowing function. Like we know that, right? Even function, odd function. How we define even signal, odd signal? X of n is equals to x of minus n. Then it is even. X of n is not equals to x of minus n. Then it is odd. But here we are not looking into that factor. We are looking into W of n is equals to W of minus n. If both are same, on what factor we are saying? We are saying that if it is it's not equals to 0. When it is not equals to 0, it can be equals to 0. When it is equals to 0, when your small n, whatever the factor of small n, we are considering. What we are considering? N less than or equals to capital N minus 1 by 2, because we are truncating into this one, right? So that one we need to consider. Equals to 0 when n greater than capital N minus 1 by 2. So by taking this factor, we are considering the windowing technique for that particular factor. So by taking that particular factor, we will find the sequence of it. So by taking that sequence, we will write the function of that windowing technique. So in that, W of n depends upon 5 types of windows: rectangular window, triangular, Hamming, Hanning, and Kaiser window. So by taking these all windowing techniques, we can able to find out the functions of that sequence. If you know the sequence, we can get the directly processing of the digital signal in your finite impulse response. So students, in today's class what we discuss about the first thing, advantages and disadvantages of your FIR filtering. Then second concept what we discuss is windowing techniques. In order to get the windowing technique, what are the steps required? First step is HD of e power j omega. What is the first step we do have to get? HD of e power j omega. How do we get HD of e power j omega? By applying HD of n. If you know the HD of n, we can find out the value of it. We can substitute that value in the HD of e power j omega. So after getting this thing, what we need to get? We need to make it into truncation. Means we need to reduce the sequence. So if you reduce it, you may get the abrupt change of the signals. That is nothing but Gibbs phenomena. In order to overcome the Gibbs phenomena, we'll apply a length of the desired sequence. Why we are applying? Because we had infinite length. We don't want infinite length, we need to make it as finite, because the third unit is talk about finite impulse response. In order to get that, we are taking n. Capital N is equals to length of the desired sequence. That n value will substitute in this small n. How we decide small n? By taking this windowing techniques. In windowing techniques, W of n is equal to W of minus n, not equals to 0. When n less than or equals to capital N minus 1 by 2, or equals to 0, n greater than equals to capital N minus 1 by 2. By looking into these things, this is just a basic. In that we had these all techniques, means for all these types of 5 types of window techniques, we will apply and we will find the desired response of that filter, desired response of that particular window, not here filter, we say that it is a window. So by taking these all windowing techniques, we will find out the response of that given specimen of the filter. So this is how we will do it, and every part of the particular filter require different formula. So that different formula you need to memorize and you need to find out, and you take the application of it for designing the FIR filtering. This is about your today's class discussion. In tomorrow's class, we'll directly reach to rectangular window and triangular window problems. Thank you. Have a good day.